Okay, guys, now we'll be looking at homework number 6. Let me make sure we are seeing everything right here. Good. And for homework number 6, we're having the focus on concepts. I think that's question 11, it says. So it says a person riding on a, let me see, this is the first one. Yeah. Okay. A person riding on a Ferris wheel. The person is riding on a Ferris wheel. When the wheel makes one complete turn, the net work done on the person by the gravitational force is what? So don't forget, gravitational force is an example of a conservative force. Is that okay? And there are 3 ways to define a conservative force. The first way is when the conservative force is doing work. When the conservative force is doing work, it is storing energy. So when you move an object up, sorry, let me silence this. Oh, I keep forgetting that. So when you raise an object up, you are storing energy. So when you let go, it does work. So that's one way to define a conservative force. Another way to define a conservative force is when you are raising the object up, gravity is going down, your displacement is up. So gravity is doing a negative work as you go up. When you come back down, on your way down, gravity is doing a positive work. So the net work by gravity on going a closed path, up, back, down, is 0. So another way to know a conservative force is the net work done when you go around a closed path is 0. So when you start somewhere from a Ferris wheel and come back to the same point, that's a closed path. A conservative force like gravity will do no work done at all. 0 work done. Is that okay? 0 work done. So when the wheel makes one complete turn, the net work done is 0. C, that's the correct one for a conservative force. Okay. The third way to know a conservative force is path independent. So when I go all the way to a mountain, my potential energy is just the change in energy from when I started and to where I ended. It doesn't care the path I took. Unlike friction, which is a non-conservative. So we're going to see all this as we go along. So next, air resistance is a non-conservative force. It always opposes the motion of an object. That's a friction. So an airplane flies from New York to Atlanta and then returns to the point of departure. So if it was a conservative force, the net work done by the conservative force would be 0. But air resistance is friction. It's a non-conservative force. So on a closed path, a non-conservative force does a negative work. So I'll tell you why. So let's say this is an object. I'm pulling this object here by a force of 50 newtons, and I have some friction here. So if I move 10 meters, so let's say friction is 5 newtons. Work done by friction is 5 times 10 minus 50 joules if I'm going to the right. Now let's switch to the left. I'm going backwards now. So my 50 is here, my 5 is here. I move 10 meters back to where I came from. Direction has flipped again. Friction is always opposite. So I'll still get minus 50 joules for friction. So my total work done will be minus 100 joules in both cases. When I go minus, when I come back, friction with flip sign also minus. I will keep getting minus. I never get 0. Unlike gravity. When you are going up, gravity is opposite your direction, negative. When you are going down, gravity is in the same direction, positive. Then you have minus, plus, you have 0. But a non-conservative force like friction, air resistance in this case, is always negative work done you're going to get. So the correct answer there is B, the second one in this case. Okay? The other ones are wrong. Okay. The next question says a toy car, 0.5 kilograms, runs on a frictionless track and has an initial kinetic energy of that. So you have this initial kinetic energy. That energy can be converted to potential energy. But you cannot convert to more than you already have. So we have to do MGH for these different heights and see which one is less than this kinetic energy. Anyone less than this kinetic energy, he can go through. Anyone more than this kinetic energy, he cannot pass. He cannot go up that height. Okay, that's the trick. So if you do MGH for 0.1, you see it's less than 2.2. 0.5 times 9.8 times 0.1. Let's do that. Let's see MGH for A. So MGH for A will give us 0.5 times 9.8, which is 4.9. times 0.1, 0.49 less than 2.2. So he will go, he will pass through A. Let's see B, 0.5 times 9.8, 4.9 times 0.2, 0.98 less than 2.2. He will go through. Now let's see C, 0.3 times 0.5 times 9.8, 4.9 times 0.3 mgh, 1.47 less than 2.2. We'll go through. Let's see 0.4, 0.5 times 9.8 mgh, 4.9 times 0.4. 1.96 less than 2.2. Now let's see 0.5. So 0.5 times 9.8, 4.9 times 0.5. 2.45 greater than 2.2. He cannot climb this one. So he can climb A, he can climb B, he can climb C, he can climb D, but not E. So the correct answer is the third one. A, B, C, D. The correct answer is D. A, B, C, and D. He cannot climb E. Okay. Let's go to the next problem. So the next problem says, in which one of the following circumstances does the principle of conservation of mechanical energy apply, even though a non-conservative force acts on the moving object? So when you have a non-conservative force, normally your energy is not conserved. So I'll tell you what is going on there. So the whole story starts from your kinetic energy equals net work done. Kinetic energy equals net work done. And net work done is work done by all the forces, conservative and non-conservative. So when non-conservative forces are negligible, kinetic energy, just change in kinetic energy they call it, sorry, equals work done by conservative forces only. Is that okay? And we know work done by conservative force, like gravitational force, is minus potential energy. Minus change in potential energy is work done by conservative force. So it means change in kinetic energy is minus change in potential energy. So change in kinetic energy plus change in potential energy equals 0. This is the conservation of mechanical energy. It only exists when non-conservative forces are negligible. Is that okay? Now, how do you write this? Change in potential energy, this is half mv final squared minus half mv initial squared plus mgh final minus mgh initial equals 0. So this is change in potential, this is change in kinetic. So when you rearrange, you have it that half mv final squared plus mgh final equals half mv initial squared plus mgh initial. So this is another way of writing the energy conservation. Total initial mechanical kinetic plus potential equals total final mechanical kinetic plus potential. Is that okay? So we are conserving mechanical, not kinetic separately or potential. The sum is mechanical. So we conserve mechanical. Total mechanical initial equals total mechanical after. So now they are telling us, is there any other circumstance that you can conserve mechanical energy even where you have non-conservative forces? Let's take a look. Ordinarily, no, but let's see. The non-conservative force has a component that points opposite to the displacement. No, opposite, you're going to get a minus work done, so it will affect. The non-conservative force points in the same direction, you're going to get a positive work done, it will affect. The non-conservative force has a direction that is opposite to the displacement, the same. Has a force that is perpendicular. Once a force is perpendicular to your displacement, that force is neglected. It does no work at all. So that is the only other condition you can have. So I think D is the correct answer. Is that okay? Where it is perpendicular, you know, when a force is perpendicular to displacement, the angle is 90. Work done is force times distance cos theta. Cos 90 is 0. So the perpendicular force will do no work for a horizontal displacement. A vertical displacement, a horizontal force will do no work. Once you're perpendicular, it won't work. But if you're at some angle, you can find cosine of that angle. You can do some work, some component of work in that direction. Some component of force in that direction, we do a work in that direction. Because work is a scalar. Work is scalar. Work has no component. It is the force that has component, or the displacement that has component. Okay. Now, let's go to the next problem. It says a 0.6 kilogram baseball or basketball is dropped out of a window that is 7 meters above the ground. The ball is caught by a person whose hands are 1.62 meters above the ground. So this is 1.62. This is 7 meters. How much work is done on the ball by its weight? So when it's falling down from here to here, how much work is done by its weight? So the distance traveled, the weight is going down, so they are both positive, so the weight is going to do a positive work. And the work done by the weight is going to be mg, the weight itself, times this distance, which is 7 minus 1.62, okay? So let's take a look at that. Seven minus 1.62, that's the height, 5.38 times the weight, 0.62 times 9.8. 32.7 joules. So it's going to do, work done by gravity is mg times h, positive because they're in the same direction, 0.62 kilograms times 9.8 times the h will be 7 minus 1.62. That's the height it fell through, okay? And that will give us the exact answer, that is 2.7 joules. So the B part says, what is the gravitational potential energy of the basketball relative to the ground when it is released? So when it is released, the gravitational potential energy is just mgh. So mgh when it is released, h this time is 0.62 times 9.8 times 7. Is that okay? So when you do that, 0.62 times, when it is released, that is the height, so you have 0.62 times 9.8 times 7, 42.5. So 42.5 joules. Then the C part is when it is caught. So when you catch it, mgh is just from the bottom, not for just potential energy is always calculated. Gravitational potential energy is always calculated with the height from the bottom. So it's mg. I'll put hf here. The one here, this capital H, the one called h naught in the diagram. So it is just 0.62 times 9.8 times 1.62 meters. So that one, and that will just give us what is it called? 0.62 times 9.8 times 1.62. So let's do that. 0.62 times 9.8 times 1.62. 9.8, correct, 9.8 joules. And then the last problem says calculate the change in potential energy, PE final minus PE initial at that point. So PE final is this B part, this PE final. PE initial is this part. So the C part is the final when it was caught, the initial is the B part when it was released. So PE final minus PE initial becomes 9.8 minus 42.5. So you're going to have a minus answer, minus 32.7 joules. So the final minus initial gives you your change in potential energy. So that's how you get that part right there. Let's go to the next problem. It says the skateboarder in the drawing starts down the left side of the ramp with an initial speed of 5.5 meters per second. Neglect conservative forces, or non-conservative forces such as friction and air resistance, and find the height h. So he started from here with some speed. How much height will he have based on the kinetic energy to clear up there? So we're going to do conservation of mechanical energy for this problem. We're going to see how that's going to help us right now. So we have half mv initial squared plus mgh initial equals half mv final squared plus mgh final. Total mechanical energy before equals total mechanical energy after. So he started from here. We can have that h final minus h initial. H final minus h initial equals, I'll do this, mgh final minus h initial equals half m v initial squared minus v final squared. So I'm combining the velocities and combining that. So I cancel all the m's. Okay. So h final minus h initial, which is what we are looking for, which they call h, the final height minus the initial height, which is h, equals half v initial squared minus v final squared divided by g. But he's going to stop there. So the v final is 0. He's going to stop at that height. So the final velocity is 0. It only has initial velocity here. So this is just v initial squared over 2g. So v initial is given 5.5. So this is 5.5 squared over 2 times 9.8. That's what we have. Let's do that and see if we get the correct answer. Okay. 5.5 squared divided by 2 divided by 9.8. 1.54 meters. Simple. 1.54 meters. Exactly what we have there. Very simple case. Conservation of energy. Okay. Next problem. So it says a slingshot fires a pebble. 6 problem 39. Fires a pebble from the top of a building at a speed of 16 meters per second. The building is 29 meters tall. Ignoring air resistance, find the speed with which the pebble strikes the ground when the pebble is fired horizontally, vertically, straight up, and vertically straight down. So this is a very tricky problem. You're going to see you're going to have the same answer for all three. Horizontally, vertically, straight up. And you'll be like, wow, what's going on? So the law of mechanical energy conservation will solve this problem quickly, but I will still solve the problem using our knowledge from projectile motion, and you see that you get the same answer whatever you do. So let us use energy to solve the problem first, okay? So solving the problem with mechanical energy, it doesn't care. Remember, mechanical energy, gravitational potential energy doesn't care about the path, whether you go up first. It just cares about where you start and where you end. So long as you start from the top of this building and you end at the bottom, you start from the top and you end at the bottom. Whether you go straight down, whether you go horizontally, whether you go up first and then come down, you are going to get the same answer from the law of conservation of mechanical energy. So it says half mv initial squared plus mgh initial equals half mv final squared plus mgh final. So mgh final is 0 because you're on the floor. You have mgh initial. They're asking you for mv final velocity. So cancel all the m's. So you're going to have it that v and multiply by 2, v initial squared plus 2gh initial equals v final squared. So when I multiply by 2, 2 comes in here, and the half goes away from here. And this one is already 0 for h final when it lands the ground. So what do you have? V final becomes square root of v initial squared plus 2gh initial. And this solves the problem. Is that okay? This solves the problem. So the initial height you started from was 29. So this becomes, and the initial velocity you are given is 16. So 16 squared plus 2 times 9.8 times 29, square root of that, will give us our final velocity with which it strikes the ground. Let's see if that gives us 28.7 that we have here. So we put in those numbers, 16 squared plus bracket open 2 times 9.8 times 29, bracket close, gives us 824.4. Let's take square root of that. 28.7 meters per second. So according to conservation of energy, irrespective of the path I take, so long as I start with the same velocity and end at the same point, I'm going to get the same answer. Now I'm going to solve vertically downward separate. I will solve horizontally separate. I will solve vertically upward separate using our knowledge from projectile motion. And we'll see we get the same answer too. So let's start. So now let's start with vertically downward. So when I strike vertically downward, my V initial is 16 meters per second, okay? So I'm doing the vertical first. Vertically downwards, okay? So I'm looking for my V final. So my V final, and I'm giving the height. So this is just going to be V initial squared minus 2G H final minus H initial. Remember? Using my kinematic equation. So this will give me the same answer. Because H final is 0, minus minus become plus, I will get the same answer I got before for when I shoot vertically straight down. V initial is 16. Exactly what I got before. Now let's do vertically upwards. So when I shoot vertically upwards, it starts with 16, it goes up to 0, it comes back. When it gets here, it is still 16, the same level. It starts falling with 16 down. So it becomes exactly like this guy from here. So I will do the same thing, I'll get the same answer. The only one that's confusing is the horizontal. So when I shoot horizontally from the building, it's supposed to go like this and strike the ground like that, okay? So it goes like this and strikes the ground. So one thing you need to understand is it doesn't strike the ground vertically. It strikes the ground at some angle. So you have Vx final and Vy final. You have to find the net for horizontal. So this is the confusing part. But when you find that net, V net, you figure out it is still the same. So when you strike horizontally with 16 meters per second, gravity doesn't affect horizontal motion. So your Vx final is the same as your Vx initial, which is 16 meters per second. Your Vy initial is 0 because there was no initial horizontal vertical velocity. But let's get our Vy final. So I can get it from the H. Vy final squared is Vy initial squared minus 2G H final minus H initial. So Vy initial is 0, Vy final squared just becomes 2GH because this is minus becomes plus. So it's just 2 times 9.8 times, it is just going to give you this part of the equation. But your Vx is the same as 16. That's the this part of the equation. When you find the net, you square this, square that, and find square root, and that's what you're going to get. Is that okay? Is that okay? Because this is Vyf square. So when you square Vy final, you get this part. Your V initial squared is the same as Vx squared. You're going to just get the same answer basically. So it's correct. Whether you solve with projectile motion, whether you solve with energy conservation, you're going to get the same answer. Okay, let's go to the next problem. Oh, sorry. I missed problem 6, chapter 6, problem 46. Okay? The pendulum problem. So it says a pendulum consists of a small object hanging from the ceiling at the end of a string of negligible mass. The string has a length of 0.7 meters. With the string hanging vertically, the object is given an initial velocity of 1.3 meters per second, parallel to the ground, and swings upward in a circular arc. Eventually, the object comes to a momentary halt at a point where the string makes an angle theta with its initial orientation, a vertical orientation, and swings back downwards. Find angle theta. So this is very simple. So you push with some velocity, the pendulum swings here to some height, h. So we don't know what h is, but I know the length of the pendulum. This is also the length of the pendulum. So this, they ask us to find theta. So cosine theta is adjacent, L minus h. L minus h is my adjacent over hypotenuse over L. So I know that. All I need to do is find h. I can get h because I know the kinetic energy here, half mv squared equals the potential energy mgh, where the final velocity was 0. So there's no kinetic energy there. And there was no potential energy here because it started from 0 height. So I only have kinetic energy converted to potential energy. So from here, m cancel m. H is just v squared over 2g. So what is v squared over 2g? 1.3 squared over 9.8. 1.3 squared over 9.8. That is h. So let's get that. 1.3 squared divided by 9.8. 0.172. So I put it here because I know L. L is given to be 0.7. So cosine theta is 0.7 minus 0.172 over 0.7. So 0.7 minus that is that divided by 0.7. So it's 0.75. So this is 0.75. 0.7536. So let's get the cosine inverse of 0.7536. That's our theta. So cosine inverse, shift cosine of the answer, 41. That's what I'm getting. Let me see if I missed something. Oh, I didn't put 2 here. 2g. V squared over 2g. 1.3 squared over 9.8 times 2. So let me do that. 1.3 squared divided by 9.8 is 0.172. But I have to divide by 2 also. 0.086. So this is supposed to be 0.086. So 0.086. So 0.7 minus 0.086 over 0.7. That becomes the correct thing to do. So 0.7 minus 0.086 divided by 0.7. So that will give us 0.877. 0.877. So let's get the cosine inverse of 0.877. So cosine inverse of 0.877, 28.7 degrees. So that's the correct answer. 0.877. So 28.7 degrees. So always watch your calculations and make sure you're doing the correct thing, and make sure you are not missing anything in the way. Okay. Okay. I don't know if you guys saw. So I started from here, kinetic energy, potential energy. I got my H, and cos theta is L minus H over L. From there I got theta. Okay. Next problem. Bicyclist, problem 63, chapter 6. Bicyclists in the Tour de France do enormous amounts of work during a race. For example, the average power per kilogram generated by Lance Armstrong, that's his mass. So we're given 66.5 watts per kilogram. So that's the work the power he has. So we can get his total power by multiplying his mass by the power per kilogram. So if I have a power per kilogram, so his average power is the power per kilogram 6.5 times his mass 75. So this will give me watts. So this is watts per kilogram times kilogram. So this kilogram, this watts per kilogram. So I have my watt. So that's power. So we say, how much work does he do during a 145-kilometer race in which his average speed is that? So I'm given the speed and distance. So I can get time, because work divided by time is power, average power. So now let me get time. So time is distance over time is speed. So time is distance over speed. Is that okay? So distance is 145 kilometers, 145,000, divided by speed is 11.8 meters per second. So this will give me the time. Is that okay? So let's do that. 145,000 divided by 11.8. 12,288.14. 0.14 seconds. Okay? That's a lot of time. 12,288.14 seconds. So work done becomes average power times time. So we have the average power. So work done, the average power is 6.5 times 75. That's the average power times time, times 12,288.14. Okay? So let's see what that gives us. 5,990,466. 5,990,466 joules, exactly. 5,990,466 joules, exactly what we have there. Now the next one is express this in calories if 1 joule is 2.389 times 10 to the power minus 4 calories. So just multiply this by 2.389 times 10 to the power minus 4 and you're going to get 1431 calories. Okay, as simple as that for the P part. Okay. Okay, next problem. You are walking out on a rowing machine. Each time you pull the rowing bar, which simulates the oars towards you, it moves a distance of 0.9 meters in this time. So you have this power, you're asked to find the force. So force times distance is your work done. Force times distance over time is your power. So we are done. Is that okay? Work done over time is power. So from there you can find your force, since you are given the distance and the time and the power. So work done per unit time is average power, and work done is force times distance. So force times distance over time is power. So I'm giving the power to be 95 watts, is force times the distance is 0.9 meters, over the time is 1.6 seconds. So my force becomes 95 times 1.6 divided by 0.9. And that problem is solved, okay? So let's do 95 times 1.6 divided by 0.9. 168.9. Exactly what we have there, 168.9 newtons. That's for chapter 6, problem 64. So let's go to focus on concept question 01. So it says two identical cars are traveling at the same speed. One is heading due east and the other due north. So identical means they have the same mass and they have the same speed, but they have different directions. So which statement is true? They have different kinetic energies? No. Kinetic energy is a scalar, so they'll have the same kinetic energies. The same momentum? No. Momentum is a vector, so they'll have different momenta because of their directions. So momentum is mass times velocity. It's a vector. Kinetic energy is half mv squared. Is a scalar. So they will have the same scalar, but they will have different vectors. They have different kinetic energy? No. They have the same kinetic energy and the same momentum? No. The same kinetic energy but different momentum. D. That's the correct one. The last one. Okay. Next. A high jumper clears the bar and has a downward, that's a focus on concept question 05, and has a downward velocity of -6 because it's downward, negative, just before landing on air mattress. So it starts, when you jump, you start with a velocity, you go 0 and then you fall back. So your change in momentum is your initial velocity minus your final velocity as you fall, multiplied by your mass. Is that okay? So your final velocity minus your initial velocity times your mass. So the mass of the high jumper is given. What is the magnitude direction of the impulse that the air mattress exerts on her? So let's first of all get the impulse he exerts on the air mattress. So that's the first thing we're going to get. The impulse is changing momentum. So impulse is changing momentum. Impulse is change in momentum. So what is the change in momentum? Mass times V final minus V initial. So mass is given to be 48.5 kilograms. V final is -6 meters per second. -6 meters per second. Minus V initial is 0 because he's falling from that height when he gets the momentum. So this is minus 48.5 times 6 with a minus sign. So let's see what that gives us. 48.5 times 6, 291. So minus 291 kilogram meters per second, or if you like, Newton seconds, the same unit. That is the momentum he exerts on the mattress or on the where he falls down. Is that okay? But how much does the mattress exert back on him? So upward is positive. So this is the one he exerts on the mattress, the negative one. The mattress will exert the same thing from Newton's third law of positive, 291 kilogram meters per second. So that's the impulse the mattress will exert on the guy. That's the answer right there. So 46.8, chapter 7, problem 01. 46.8 kilogram scalar is standing at rest in front of a wall. By pushing against the wall, she propels herself backward with a velocity of -1.31 meters per second. Her hands are in contact with the wall for 0.732 seconds. Ignore friction and wind resistance. Find the average force she exerts on the wall. Is that okay? Which has the same magnitude but opposite direction as the force the wall exerts on her. So let's do that. So we're going to have change in momentum again as impulse, but this time around we have to put in the formula of impulse. Impulse is force times time. So force times time equals change in momentum. Is that okay? So now she propels herself backwards with earth velocity and her hands are in contact with the wall for that time. So let's get the change in momentum. So the change in momentum is her mass, 46.8, times her final velocity, minus 1.3, minus initial velocity is 0. So she starts from 0 and propels herself to that speed. Is that okay? So what is her final impulse? Is that okay? Let me see. Okay. So from here, we get 46.8 times minus 1.31. So what does that give us? (1.31 times 46.8). 61.308. Okay, let's fix this here. If she propels herself, so this becomes her initial velocity, and we'll say her final velocity is 0. We can switch that. Minus the initial velocity 1.31. Okay, so this becomes plus. So that will give us 61.308. So now let's get the force times time. The time is given to be 0.32732. So the force becomes 61.308 divided by 0.732. And that will give you 83.75 as the force the wall exacts on her. Is that okay? You could do the same thing I did before and get a minus, but you're going to get the force she exacts on the wall. The force the wall exacts on her, which is towards her direction, which is negative. But the wall, the force that she exacts on the wall, she's pushing on the wall to go on the positive side. That she's pushing on the wall, positive, and then she propels to the negative side. Okay? Okay. Next problem. Problem 02. A model rocket is constructed with a motor that can provide a total impulse of 40 Newton seconds. The mass of the rocket is that. What is the speed that this rocket achieves when it is launched from rest? So it is launched from rest means initial velocity is 0. Now we're looking for final velocity. We are giving our impulse, which is the product of force and time, to be 40. So we are giving the mass to be 0.195. Final velocity minus 0. So we can find final velocity to be 40 divided by 0.195. Simple as that. Okay. And that should give us the answer we have there. 205 meters per second. Chapter 7, problem 7. It says a hockey goalie is standing on ice. Another player fires a puck, mass that, at the goalie with a velocity that. If the goalie catches the puck with his glove, so when you catch it, the velocity goes to 0. In that time, what is the magnitude of the average force exerted on the goalie by the puck? Okay, so let's take a look at that. So the same thing. Impulse equals change in momentum. Is that okay? The puck is 0.17 mass. Final velocity is 0. Initial velocity is 45 meters per second. Is that okay? So we are given the time, we're looking for the force. The time is 5.59 times 10 raised to the power negative 3. So what is the force? 0.17 times minus 45 over 5.59 times 10 raised to the power negative 3. That is my force. But what force am I getting from there? Is that okay? This force that I'm getting from here is going to give me a negative force. So the puck is moving in a positive direction. So when you catch the puck, is that okay? The puck is gonna have a positive force on you. You are gonna have a negative force on the puck, since the puck is the one traveling in the positive direction. So whatever answer we're gonna get here will be the force you exert on the puck. The puck we exert the positive of that answer on you. Is that okay? So we're gonna have 0.17 times 45 divided by 5.59 times 10 to the power minus 3. So that becomes 1368. Is that okay? 1368.5. 1368.5 newtons. So this was minus, but we're looking for the force the puck exerts on you, so we're going to put the positive sign in there. Is that okay? So we're going to put the positive sign in there for that one. Okay? Okay, let's go to the B part. Is that okay? The hard part. The B part now says, instead of catching the puck, the goalie slaps it with a stick. So now we're going to have a V final and returns the puck straight back to the player with a velocity of negative 45. So the V final is negative 45. So now let's solve the problem again. The same time, now let's find the average force. The same time. So now we have a V final. Instead of 0, he's catching it. He's applying negative 45 meters per second. So negative 45 minus negative 45, negative 90. So my force now becomes 0.17 times negative 90 over 5.59 times 10 to the power minus 3. And don't forget, the negative is for the force you apply on the puck. The force the puck applies on you becomes positive of whatever answer we get here. So 0.17 times 90. So I'll do that on my calculator. 0.17 times 90 divided by 5.59. 2737. 2737 newtons. Positive, not negative. Okay. That becomes the answer we have here. Is that okay? All right. Next problem. And this is the last problem, I think. Yes, last problem. Thank goodness. Chapter 7, problem 6. 2 arrows are fired simultaneously with the same speed. One goes due east, the other due south. They have the same mass. What is the magnitude of the total momentum? So momentum along x, momentum along y, you find the net momentum. So using your vector notation principle, okay? So that is what happens here. So they have the same speed and the same mass. One going due south, so one is going down with a velocity of 30 meters per second and a mass of 0.1 kilograms. The other one is going due east with the same velocity, 30 meters per second, 0.1 kilograms. So mass times velocity is the momentum here, which is 30 times 0.1 is the px, 3 kilogram meters per second. Py is also the same thing, 3 kilogram meters per second when you multiply 30 times 0.1. So you're going to find the net. What is the net? Remember? From vectors. So 3, what is the net? 3 squared plus 3 squared square root. That's it. So that's my p net is px squared plus py squared square root. Momentum in x squared, momentum in y squared square root. That's 9 plus 9, square root of 18. And that just gives you the answer you have there. 4.24 kilograms meters squared. They are waiting for the magnitude, so they don't care about the direction. Only the magnitude is fine. That's all you want. 4.24 kilogram meters per second. And that ends the homework 6, and I'll see you guys for homework 7. Thank you.